Hello, Astro people. Okay, now we have derived the fundamental law of cosines. We are one step closer to applying these laws to find the coordinate transformations between the different coordinates in use in astronomy. Before we go further, let us prove a second theorem that is going to be very important, which is the theorem of the dual triangle. The dual triangle is shown here in this figure. If you have a spherical triangle of vertices A, B, and C, the dual triangle is a triangle A prime, B prime, and C prime, whose vertices are the poles of the great circles that define A, B, C. You have here the side AB, draw its great circle, and the pole of this great circle, right? You have one pole here, and you have the other pole here. That's the C prime. So the point C prime is the pole of the great circle of the side AB. On the same token, you have here the side AC. Draw the great circle of the side AC. Its pole is the point B prime. And here you have the side BC. Draw the great circle of BC. The poles are going to be the point A prime and the opposite point. So you can draw this triangle whose vertices are the poles of the great circles that define ABC. That is the dual triangle. Little a prime is the side opposite to big A prime. Little b prime is the side opposite to big B prime, and little c prime, the side opposite to big C prime. The relation that we want to prove is that little a prime, the side of the dual triangle, is equal to pi minus the angle A of the original triangle. And it defines a relation between a side in the dual triangle and an angle in the original triangle. And this relationship is useful because here in this case, we have the fundamental law of cosines that is relating three sides and an angle. You can use the relationship given by the dual triangle and relate the sides to angles. Resolve the pi minus the angle to the angle using the unit circle, and then you can convert that into the fundamental law of cosines for three angles and the side. So let's see how we can prove this rigorously. So given that A prime, B prime, and C prime are the poles of ABC, then A prime is on the equator of A. You see this because the point A, which is here, is separated by B prime and C prime by arcs of 90 degrees, since they are the poles. If this is a 90-degree arc and this is a 90-degree arc, then, being the poles, this side here, A prime, must be an equator. So we can prolong the arc AB until it hits the equator at the point P, and prolong the arc AC until it hits the equator at the point Q. So the angular size of PQ is equal to the angle A, because the angle PAQ is the same as the angle BANC. Now, Q is on the equator of B prime. You can see this because B prime connects to A, and B prime also connects to C through 90-degree arcs of great circle. So B prime is the pole of A and C, and Q is the prolongation of A and C. So Q must lie on the equator of B prime. So if Q is on the equator of B prime, then the arc QB prime must be equal to pi over 2. Now P, by the same token, is on the equator of C prime. So if P is on the equator of C prime, then PC prime is also equal to pi over 2. Now, by geometrical construction, this arc BC prime is equal to B prime P plus PQ plus CQ prime. It's BP. It's B prime P prime plus PQ plus QC prime. So we can group together B prime PE plus PQ as QB prime. And QB prime is equal to pi over 2. Also by geometrical construction, PC prime is equal to PQ plus QC prime. So we can isolate QC prime as PC prime minus PQ, and PC prime is equal to pi over 2, and PQ is equal to A. So we have these two relationships, one for B prime C prime as a function of QC prime, and this QC prime relationship, which is equal to pi over 2 minus A. If you substitute 2 into 1, then you have that B prime C prime is equal to pi over 2 plus pi over 2 minus A. That is, it's equal to pi minus A. And B prime C prime is the side A prime. Therefore, you find the relationship you're wanting to prove. A prime is equal to pi minus A, the theorem QED.